okay. So I want to show you now, which I briefly touched last time, but I want to explain you how our ability to have switches and ability to add capacitors can completely change operation of the transformer. Here, this is an auto transformer, non-isolated, but nevertheless, it is a transformer with a primary and secondary. And some people looked at that, so, oh, well, that's just like if you eliminate, let me see. If you eliminate this switch and eliminate this capacitor shorted, what is this? This is stepped inductor buck, nothing, and nothing new, existed for 50 years. However, I just want to demonstrate you. If you know what you're doing, and if you introduce right components and right place, like in this capacitor in this place, and this switch, extra switch here, then you completely change operation of this magnetic structure. I call this magnetic structure hybrid transformer because it has, as you see, when the switch is on, it has a square wave voltage, input voltage minus output voltage. That's the voltage across the primary, so the square wave voltage across this switch. Now, we just touched upon why the leakage inductance in 60 Hertz is actually desired. What will happen with the leakage inductance here? In original buck converter, tapped inductor buck, without this capacitance and without this switch, you have a switch on and switch off. What happens with this leakage inductance? Energy is stored in that leakage inductance as LR I peak square, so it's energy stored, and then times the switching frequency, how many cycles, that is the power. So you lose a lot of power due to energy stored in leakage inductance. Okay, so you say, well, I'll just make it tight coupling and like 1 turns and foil and then 10 turns on top of it and hope for the best. Well, that won't work because when it's multiplied with a very high frequency, it's going to be a lot of loss, 10%, 20% of the power lost in here. You don't want that. Now the question is, can I make now the transformer, which is actually using this leakage inductance as the part of the circuit and make sure that I make this resonance on the input circuit is this waveform here. So I make this resonant, this leakage inductance, which is undesirable. I make it resonant with these capacitors at the certain frequency, which is here. And do you agree that if this is capacitance on a primary, the same as in a true converter, capacitor on a primary doesn't allow DC current in this capacitor, so the current in this here will have a zero average. It means that during the time that this switch is on, there will be a power transfer this way, but then when this switch is off, during off period, and this one is conducting, in this thing here, there is a primary current during off period, or off period of main switch and on period of this switch. During off period, let's say 90%, this would be resonant current established with these two. Why? Because it turns out you will operating with the dot connection in such a way that this will be shorted. This transformer from primary to secondary with such dot connection will be shorted. So this will be resonant current on the primary. And you know why is that important? because that means this current on the primary, that is a current, okay. That is a current on the, let me show you here. So this current here is a current in yellow. It is a sum of primary current, which is this current, and a secondary current. And what is secondary current? This is a transformer. So if it has a primary current, sine wave, the secondary current will have to be also sine wave. You can see it during off period, multiply with the turns ratio. So that means if this is 2 to 1, this with twice larger sine wave current compared to input. But this sine wave current also has a DC current drawn in the load. So there'll be DC current in the load, which is added to this sine wave current. But both of these sine wave current through the primary and sine wave current through the secondary red, these green and red waveforms add together. In fact, I should have, I guess, use my, let me see. Come on. What happened? Okay. Why doesn't, see, that's nice to have a razor, right? Okay. So now this green waveform, and let's put it here this way. So we have now this situation. This green waveform is this current going here, and then the red waveform is this current coming here, and and then the diode current is this sum of the current. And what is the beauty now? I'll give you the kind of anecdote about inductance, okay? Can you see it now? You see what I'm having, right?
Yes, you can see your screen.
Okay, yeah. Back in, there's another anecdote and history. In 1831, Faraday disclosed its law of electromagnetic induction. In 1830, Joseph Henry was professor of Princeton University, and he came independently to Faraday's law, but he didn't publish it, and then Faraday got all the credit. Many years later, Henry also worked in this field, in fact, on telegraphy and so on, and even had some patent disputes with Bell and so on. But the point being is he was at some lecture that someone, at that time, they tried to use this wireless transmission, and Tesla worked with this as well. And then they were using a way to create the sparks. They needed to create the sparks on a transformer and so on. So they tried to do the spikes, and they couldn't generate it. They were disconnecting the circuit to generate the spikes using this inductance, but it just wasn't good enough. Then Henry was in the audience, and he came and he told them, oh, they made inductance, and he used the wire that was used to make inductor and make 10 times more turns. And when you make it 10 times more turns, inductance was increased by turn square, so you had 100 times more inductance. So now if you turn a switch on and off into inductance, sure, you're going to have a big spark, because that's what it is. You are discharging that energy stored in inductance in that spark, okay? But this is opposite what we do here. What happens if I turn the switch on and off? You see, these switches are changing time from being on to off and from off to on. These are two instances when you are turning on and off switches. What happens if the current in this yellow waveform is current in the diode? What happens if the current in the diode is at zero current here and zero current here? Would you mind the inductance, leakage inductance is absorbed in operation of converter. there are no losses, both turn on and turn off losses. And if you make your converter now not to regulate with the duty ratio control, but regulate with the switching frequency, you can force this off period to be constant, and then you change the switching total switching period, which is effectively changing duty ratios. You can regulate and still have, for any operating point, input voltage and operating load current, you still have the same no losses on the diode. It is zero switching losses on the diode. Now, how good is that? What's even better that you can even appreciate. Why? Because if this is now the first converter which operates with a voltage to current. It is not voltage to voltage converter. It is the output current, which is this resonant current here. It has a DC level, and the output current, this resonant currents depend what kind of a peak resonances will be imposed on a diode and imposed on a primary. That means the current, DC load current, dictates the peak resonances. So if now DC load current is dropped in half, all these magnitudes will drop in half. Well, that's exactly what you wanted to do for a microprocessor drive when you have a change of DC load current, sudden change, and then you have immediate change on the next cycle of waveforms drawn from a converter. That's one thing. The other, it is staying at zero current level even at that point. So you can go from a full load to no load. You will not go in a different mode of operation. There is no discontinuous conduction mode. You understand? It was always in continuous conduction. How good is that? Better than you can even imagine. Because why? Once you are in a continuous conduction at no load to full load, you don't have the duty ratio to compensate for change of mode operation, like in the back boost and flyback, that it drastically changes voltage conversion ratio. So now you have a feedback. You don't need a feedback. Why that is good? Well, it's even better, because if you don't need the feedback, then you don't need the limitation of the bandwidth. So your full bandwidth of switching frequency is available. Whereas if you have a feedback, you have in addition the bandwidth limitation. That bandwidth of converter is at best 10% of the switching frequency. So you have 10 times lower bandwidth, and you have no way to allow for quick change of the current, and it's disaster. And what's the solution of our power management companies? Use not one buck converter, use 12 buck converters in parallel to try to operate, to drive a microprocessor drive at 1 volt, from 12 volt to 1 volt. So I always used to say, 1 buck converter is bad enough because it stores energy, as I explained last time. Now you use it 12 times, and you use a special digital circuits to operate this in parallel, right? So how smart is that? Not too smart, right? And are they going to give up on their? No, because they have a business there. They have a business, and they are competing for a $10 billion market a few years ago when I looked at it. And out of this $10 billion market, each of these 50 power management companies make their own version of the 12 buck converters for Intel and all the other IC companies, big microprocessor, and they're all happy. They have 5% of the market, and they don't want anything better, you know, because no one else is better. Their competitors are just as bad as they are, and they are happy to share whatever money they get, okay? And life goes on, okay? So, all right. Hopefully, you'll change that in due course. Now, let me now explain how you can understand this circuit. I try to give you the global picture, and the global picture here is this. Does this transformer as a device has to operate as a square wave voltage and square wave current? I did that in a true converter 45, 46 years ago, but it doesn't have to be. Now I'm showing that for the first time, look, for the first time, we are able to take care of a transformer that its built-in leakage inductance is not the problem, it is a solution. You see what I'm saying? Because in all other converters which have isolation transformer or tapped inductor or you name it, look, without this capacitance and without this resonance, just this switch and this in a buck, energy stored in leakage inductance will be huge. And at the moment of switching, there'll be huge jump in the current, and that jump in the current must be killed by some kind of a very fancy snubber to kill all that leakage energy. And that won't be pretty. And it won't lost a lot of time and a lot of bad waveforms. Here, you have, isn't that beauty? You have a transformer, which unlike a Faraday, or Tesla, Faraday's original idea, or actually Tesla's in an AC generator in AC current, it has a square wave voltage drive and sine wave current, both primary and secondary, and this switch now is forced to have zero switching at all operating points. And then, of course, there's a way that we can make this at the zero voltage high switching, and then you have now another benefit, and you can operate. Listen, you can now operate when you are at 99% efficiency. You don't need to regulate with the duty ratio because it's automatically giving a good regulation, no change of operating point. So you can operate it open loop, no stability problems, no bandwidth limitation, no change of mode of operation. Oh, one more thing, I forgot. What will happen if I put two converters like this next to each other, operating from the same source and to the load, but this converter is identical to this one here, but what? It's made to be delayed from the first one by 50%. So one current will be this yellow and the other current will be this yellow. If you add them together, what are you going to get? Small ripple current. So how is bad? From something, two converters, not 12 buck converters, two of these identical converters. We have a pin, sync pin, which says one is sync for half a period from the other. What do you get? No capacitors needed on the output. How good is that?
Some are required, but like way less than usual. Just
and even better. What is even better?
Yeah.
Oh, listen, what is even better? What about this capacitor? Does it have to be large?
No, actually, yeah, like 2.2 microhenries, microfarads.
The point is this we have to talk about these capacitors in terms of its voltage rating, DC voltage, and in terms of this RMS current. Now, what about RMS current here? If this is a 10-to-1 step down in the voltage, this is 10-to-1 step up in the current, which means opposite, it is 10-to-1 step down in the current from this 100 amp, this becomes now 10 amps. So this capacitor delivers 100 amp output, actually more, 200 amp, because two of them in parallel, each one will be delivering 100 amps, so it's 200 amps, but this capacitor will be 10 amps. What about its voltage? If this is 100 volts, doesn't have to be, it's not 100 volts because this capacitor will be D times VG. So its duty ratio is 0.1. This capacitor will be 10 volts. So its magic happens. Capacitance is rated as power 10 times less than input voltage, 10 times less than output current, so 100 times in power and carrying 100 times higher power. So how bad is that? Okay. So I'm telling you the importance of converter system, or topology and mode of operation. The hybrid switching, what I call this, and hybrid transformer, this is it. And it has why I call it hybrid switching and hybrid transformer. Have you ever seen a converter with the 3 switches? I worked with my PhD student back in Caltech when we originally started assuming that All converters come because you have inductors and capacitors like in a true converter. So while inductance is storing energy, increasing current, capacitor is releasing energy, discharging. So they work in unison. Store, restore, charge, discharge the current, and charge, discharge the voltage, and so on. So we never even considered 3 switches. Here is an example that the 3 switches are actually beautiful, right? It's not like 4 switches and 6 switches, 8 switches in pair like a full bridge. 4 switches, a transistor on a primary, 4 diodes in a secondary, 8 switches. To just get isolation, it's just have 3 switches and get all of these features. Now comes what I promised, but I'm gradually running out of time. So let me finish this presentation and remind you where I'm going ahead with it. I'm just showing you that after I came up with this square wave drive or rectangular drive of current, rectangular voltage in a true converter, here's another example when a voltage drive is a square wave and current on a transformer sine wave. But what's the difference? Sine wave currents are not 60 hertz. They're 60 kilohertz. So therefore, but of course important is it is not 600 kilohertz and not 6 megahertz. I don't need that. 60 kilohertz is plenty enough. And as I mentioned last time in my presentation, we failed dramatically in the power electronics. When I started, we were excited to say, oh, we had 4 kilohertz bipolar. We can't wait to get to the 20 kilohertz. And then 50 hertz transformer to 20 kilohertz will be 40 times smaller. And then we went from 20 kilohertz because of this wrong way of fake inductors, which are not AC inductors, but DC inductors. We went to 200 kilohertz and 2 megahertz and now 20 megahertz. And did we get any reduction in size? Zilch. We increased the frequency 1,000 times and we don't have any size reduction. That's number one. But the bigger problem than that is not only we don't have any size reduction, we don't have scaling of the power. We are not allowed to scale power because we are limited with the current of these inductors, and therefore we are limited with the eventually the power we can process. And as I pointed last time, all classical converters have another big problem. They have big inductors, they store energy, like back type inductor in the output, and that energy requires that the core is 2 or 3 core sizes bigger than a core used for decent transformer. Okay? And it's not needed. And it's limiting the current and limiting power converter. Certainly, you won't be able to make a forward converter with a, even 100 kilowatt, let alone megawatt or so on, right? Because you have a current and power limitation. So let me now see the analysis of this and how this converter works, that essentially the connection you are making it, you are for certain off time period, you are making the transformer, which seems like unheard of, short. And I'll explain you why. So let me look at this. I think I can move this up at the top so it doesn't bother us. Yeah, okay. All right, so this is about 12 volts to 1. What is the other advantage? I think my title was this same, obviously, once I have a turns ratio here, I'm not limited to 12 volt to 1, right? Because I have 2 ways to step down voltage. One through duty ratio, directly proportional duty ratio. So 0.1 duty ratio will give you 10 to 1 step down. And if you have a 10 to 1 turns ratio of this hybrid transformer, that's another 10 to 1 step down. So if you have a 100 volt input, through duty ratio, you're reducing output voltage to 10 volts, and through 10 to 1 transformer, hybrid transformer, you're reducing it to 1 volt. Voila, you have 100 volt down to 1 volt. Not bad. And what this also does, what is going to be rating of the voltage rating of this device? Precisely if this is a devices are 100 volts on input, which is also an important point, This is not like in most converters, like bridge type and so on, when you have the input switches are at least 2 or 3 times higher rating the input voltage. No way. Here, the input switches only see input voltage, whether it's on and off, either one see only input voltage, irrespective of operating point. And output diode sees the output voltage divided by the duty ratio. So if duty ratio here is 50%, output voltage is 1 volt, this is going to be a 2-volt device. Okay, that's what you need for low voltage, high current, right? So you have automatic scaling. Remember how I mentioned the transformer does the beauty to automatically scale voltage and currents from primary side to secondary side and make it efficient. You know, what happens with a forward converter? Can you do that? Absolutely not. In forward converter, not only that you operate at low duty ratio, 10%, and that means you're transferring power only during 10%. The 90% of the time, you're not transferring the power. Windings are there and you are undoing the damage because you have to have a reset winding to reset the core to start back from 0 to positive flux. The same thing, if you operate a higher duty ratio on a forward converter, what happens? Your output switches, yeah, inductance on the output will be smaller in terms of the flux requirement, but the higher duty ratio above 0.5, the bigger the voltage switches on the secondary side, they are 2. So they have to be 3, 4, 5 times bigger than the output voltage. That's not good because for conduction losses. And ideally, what you'd like to have in a transformer, in a converter, is that input switches have no voltage rating higher than input voltage, output switches no higher rating than input voltage. Here it is, say, 2 times the 50% duty ratio. And you have 0 voltage switching on a primary of 2 switch devices and 0 current single device on a second. Okay? And the transformer, which is really small. So it's how small? Here is example. This will be example of that prototype that was made a long time ago. And now going to a little bit into analysis, explaining how this works. Here is, oh yeah, as I mentioned, now this is not only 12 volt to 1. Why would you need now to have a separate converter 48 volt to 12 and then a separate 12 volt to 1, right? When you can do all in one. You can do 48 volt to 1. Just announcement what is coming around the corner, you know, this is soon. And that is, we will make a 48 to 1 in a new type of a converter, which I will designate to call not Chuk buck 2. I don't want to do anything with the buck because it's so much better than a buck. And I will call it a Chuk 2, which means another Chuk converter. And that one will be not only 48 for 1, non-isolated, but will be 48 volt to 1 isolated. And if it is isolated, there's no reason I couldn't do 400 volts to 1. And why is that good? Because now microprocessor can operate 12 microprocessor, each from 400 volts with a 1 amp current, but operate at the 100 amp and 1 volt directly because there is no distribution losses because you have a single source of 400 volts supplying 12 microprocessors and directly drive them to 1 volt. In fact, higher step down, the better it is. Okay. Anyway, so this so far does work for both 48 volt as directly to 1 and 48 volt, 12 volts to 1 with a step load change in 1 cycle. Now, let me show the basic understanding here. So this is what we are facing, very simple structure. So 2 switches are operated with grounded with a high side driver. So you can have high side driver and drive them directly. You have a diode, which can be replaced with a synchronous MOSFET or a gallium nitride switch with a grounded source. So that again is direct drive and direct drive for this switch. And you have this hybrid auto transformer and you have positive output for a positive input. So it's polarity non-invariant. Now, and its operation is such that you can see the conversion is secondary side divided by totally primary and secondary side. That's one step down, and the other step down through duty ratio of the main switch. Now, if you go to operation, what happens when this switch is shorted, conducting? Then if this switch is open, the power flow is this way. You agree? Okay. But let me use my pen, and hopefully I can actually put it at the bottom so I don't. Okay, I put it at the bottom here so it's out of the way. What happens if I have? Oh, look at this here. I have now. Okay, now I discovered it's not only draw. I forgot that I have here also these pens. I thought this. Oh, I'll use the one that I have here. You have different ways, so. Okay, so what is happening when this diode, when this switch is closed? That forces the current, forces this diode to turn on. You see that? This current here forces the diode. So this is almost like a voltage bidirectional switch, active switch in series with a diode, which says that the current can only flow in this direction. In fact, it already tells you that, remember that this diode current can never go negative. So if you have a diode here, in other converters, you will, if I put a rectifier MOSFET, this can only conduct the current this direction, cannot go negative. And just the magnitude of this will be reduced. But anyway, so the point is, in this current, when this is shorted, what happens? This switch is plus and this is minus. So the output voltage V will be plus minus from this dot connection to here. But remember, the dot connection here just in such way that now, when this switch is turned on, this diode is turned on, this makes this positive voltage here reflect as a positive voltage from here to here. You see that? Positive voltage here, that's meaning of the dot connection. So positive voltage impressed here because the diode is shorted is now positive voltage from here to here with a turns ratio. And that becomes voltage source minus plus like this, right? Okay, and then in this loop, what do you have? You have this capacitor CR, you have resonant inductance LR, and you have this voltage, this voltage here, which is voltage minus plus. It is DC, it is constant voltage because its output is constant. It's voltage V. So this is what the circuit you have. So you tell me what is the voltage that has to happen into this capacitor? What this capacitor will be charged to? If this was 1-to-1 turns ratio, right? Say 1-to-1 turns ratio. So this voltage plus V will be also from here to here minus V. So this voltage is minus V, and this capacitor here in this loop. Remember what this inductance says. This resonant inductance says I have to be volt-second balanced or flux balanced during this period. I have to be volt-second balanced. Positive volt-second and negative volt-seconds have to be equal and 0. So if this is a 0 volt-second balance, then it says that if that is a 0 volt second balance, then LR dir per dt has to be equal to VCR plus minus V. So if this dr per dt has to be 0, VCR must be V. So this capacitor has to be charged to the output voltage, plus minus. So this will be V, and this voltage from here to here is V. So V minus V is 0. That's why you have a sine wave current, and everything is working fine. Okay, and that means, as you look at it, because this is a V from here, and this is minus plus V. So basically, you have really this acts like a shorted transformer, because this voltage is actually acting along with this here, makes this resonance just resonating this inductor, this capacitor, and CR is much bigger. C capacitor is much bigger than CR, so it won't affect this resonance. So this resonance is fixed, independent of the thing. So this is what is happening. VCR must be equal to VC. Capacitance C is much larger, so it won't affect the resonance time, but it will actually, DC voltage here has to be equal to DC voltage here. And during resonant times, VC is equal to VCR, and you have a clear. So it's a simple resonant circuit, equivalent circuit. And that's what we just showed is happening under condition like here. And then what is simplified resonant circuit? Well, the VCR is V sine, it has to be sine omega resonance T. And you see here that means that this resonant capacitor, as I showed, you have a voltage which is resonant is a sine wave, and the resonant current is a sine wave with a zero average. You see, it has the I cosine omega resonant T, and secondary current has an output load minus this resonant current. So superimposed, the secondary current is superimposed to DC load current, and that means that diode current is sum of these two current, and diode current is, as I said here, it's DC load current minus cosine omega RT, but cosine omega RT, sorry, this has to miss, we should have I times cosine omega RT, so therefore that is always zero, independent of the DC load current. As this load current changes, I showed last time demonstration on a spike, on a flex, that basically you drop the DC load current in half and everything drops in half, you know, and you drop to 10%, everything drops to 10%. So the point is, this is how this is incorporated in operation of a circuit. And that's operational converter, rectangular voltage and flux balance on this winding of this hybrid transformer. And this shows that this flux balance. But, and from that, I can derive the, from this flux balance, I can derive that conversion gain is 0.5 D times VG, in this case when it is 1:1. But when it is N/1 turns ratio, then it is D duty ratio step down, and ratio of the secondary to, this will be common brackets, you know, is N1 plus N2 instead of just N1. So N2 over secondary winding with the total sum of the primary and secondary winding is a step down and another step down. So it has a lot of high step down, eliminate, and the key is again, eliminate the resonant, eliminate leakage storage and efficiency problem. Eliminate the feedback and allows very wide bandwidth, And in addition to that, because you don't have a feedback and stability problem, you have wide bandwidth, but single converter has a single cycle restoration of the output. In other words, a jump of the current on the DC current on the output will result directly in a reduction of the appropriate current drawn from the source. So it is really voltage to current output, okay? And controlled by DC low current. Here is example of 48 volt to, I think, 1 volt, 100 amps. Simulation model, and let's see here. This is an example of a 100 amp diode current and DC output of 100 amp. And now you have a primary is 0 to current level, and secondary is multiplied, and it's sitting at the 100 amp DC current, and it has a 50 amp peak-to-peak current. But when you add these two ripple currents, then end up with this yellow diode current. So the diode current splits into two directions, in the primary and in the secondary, both sine wave, and the diode is a sine wave driving the primary with the sine and the secondary with the turns ratio. And what is happening now, if you have reduced the current from 200 amp peak to peak of 100 amps DC in a diode, you reduce it to 100 amp peak on a diode and 50 amp, well, everything is scaled down. So you have a transient response during switching period, or because there are two converters in parallel, at the maximum, you will have a transient happen in half of that. So if it is 100 kilohertz, that means 10 microsecond one period, two of them together will be 5 microseconds. So we'll have the maximum transient take in a 5 microsecond, but depending on which instance you take a transient, it might be a fraction of that. So you don't need 12 converters at megahertz to get a fast transient. 2 converters at 50 kilohertz is just good enough, or even better than a regular one. So that's a result of this. And optimum control method, I discussed it, optimally constant off-time control and variable frequency. But variable frequency is really like a constant frequency, because if you have a duty ratio 0.1 and you change the 90% duty ratio, off-time is 90%, and you change the duty ratio to 0.05, you have 2 to 1 step down in the voltage, but you change 10% switching frequency. So therefore, it's really constant off control, but with basically really constant, nearly constant switching frequency. Anyway, so these are results, and my time has run out. It says 10:00 a.m. Okay, so I open up now this discussion. Of course, here just you can have all